Hi, welcome to Signal Path. I have a pretty interesting episode for you guys today. I want to talk about DC-DC converters. Now, why is that such an important topic? Now, if you look at the past 10 years, the number of mobile devices and computers and cell phones and components that are on batteries has just exploded. This is not just because of IoT, it's also because we demand more and more from our mobile computers. Now, in every one of those devices, there are several key DC-DC converters that ultimately determine the efficiency and the power conversion requirements of every one of those devices. This has meant that companies like Apple and Intel and many other manufacturers have spent hundreds of millions of dollars to figure out what is the best way of integrating these DC-DC converters as close as possible to their devices. Now, of course, the knowledge and to be able to measure, understand, and design DC-DC converters is really sought after these days in the industry. So I thought it would be a good idea to do a tutorial on that. Now, it turns out that TI has made this really quite amazing lab kit for power conversion. There are several versions of this, and I'm going to talk about this in detail and show you exactly what's going on with it. Now, TI makes DC-DC converters. They're one of the leading manufacturers of these components, so naturally it's in their interest to produce something to show how DC-DC converters work. And this is not just some silly thing they've put together to promote their product. This is extraordinarily detailed. If you see how much effort that's gone into putting these lab kits together, you would be amazed. The documents are fairly advanced. They start from introductory topics going to really detailed material that unless you're in DC-DC converter design community, you may not even come across. So I'm really impressed with this, and I think it's worthwhile taking a look at it and see how it works. So let me show you what's in the kit, what kind of kits are available, and then we'll do some experiments. So this particular university program from Texas Instruments has a lot of details in it, and it goes far beyond just the buck converter lab. That's the one that I have here in my lab, which we will take a look at, but there's also an LDO lab, a boost lab, and a buck-boost lab. And each of these accompany their own document and a set of experiments and explanations, and they teach you about the different impacts of different components on the system performance, cost, noise, trade-offs, and how you choose between different architectures. And there's a lot to learn. If you essentially have all of these labs, that's a full course on DC-DC conversion techniques and power conversion techniques. Now, each of these, as I said, has its own booklet. So I want to show you what the booklet of the Buck lab, which is the one we're going to use, looks like, so you can appreciate the amount of effort that's gone into putting one of these things together. So the Buck lab has two different buck converters on it. One of them is a PFET buck controller, which is the LM3475, and the other one is a TPS54160. And the booklet shows you the details of the schematics of each of these. So if you follow through, we can see the full schematic of the LM3475, and they show you exactly the number of components that are there, what jumpers are there, and what you have to do with each jumper for each of the experiments. The list of materials, of course, is included, a close-up picture of the board showing you all the different points you can probe and what they correspond to, with full detailed explanation of every single one of the things that's here. This must have taken forever to put together. And here's the same thing for the schematic of the TPS54160. I'm not going to go into the details of this. We'll take a look at the board in just a bit. And similarly, you're going to have all the details, of course. And then once you go through all of these and some warnings and recommendations, then the experiments begin. This particular course has 7 experiments, and they get more and more advanced, looking at more and more subtle differences and subtle impacts of components on the system performance. So instead of going through this like this, why don't we just jump to the lab, hook one up, and do one of the experiments and see how it plays out. And of course, you're going to get a nice color printed version of this document as well. And here we have the setup of our first experiment. The first experiment has to do with system efficiency. So naturally, we're going to have to measure how much power is going into the DC-DC converter, how much power is coming out of it. And the easiest way to do that is to use ammeters and voltmeters, both at the input and the output. So there is an ammeter voltmeter here, ammeter voltmeter here. That's going to be able to give us power at the input and power at the output. And we're going to need a DC power supply to put energy into the DC-DC converter and a DC electronic load to dissipate energy into it. There's also an oscilloscope to measure various internal current and voltage relationships. And these transient relationships are really important. That's the insight into how the efficiency of the system is actually impacted under different load conditions. Now, here in my lab, I have access to some of the world's best source meters. So we can actually replace the DC power supply, ammeter and voltmeter by one source meter, and the DC electronic load and the ammeter and the voltmeter at the output with another source meter, because a source meter is a 4-quadrant instrument that allows us to basically use it in any of these positions and get all the information at the same time, which would significantly simplify this setup. Now, they don't use source meters because source meters are not available everywhere. The most basic equipment are shown here in order to do the same measurement. But you've seen me do teardowns and reviews of Keithley source meters, so we're going to use that. Let's go ahead and build this setup. And for those of you who want to see the board close up, look at it. It's beautiful. It's really nicely put together. Everything is evenly spaced out to make it easy for you to connect the oscilloscope's probes to completely separate circuits, so they're totally independent of each other. And in theory, you could run them in parallel. Here's a station here for all the different jumpers for you to store them so that they don't get lost, and then you can just transfer them from there to various locations. And as you saw in the document, everything is very well shown, and a detailed description is given in the document so that there's no confusion on how to set it up. Now the first experiment, I believe, uses the bottom DC-DC converter, so that's what we're going to use. Alright, here is our measurement setup. So as I said, we're going to be using source measure units in order to provide power to the DC-DC converter and act as a load. We also need a couple of other measurement instruments. So to view the waveforms going through the DC-DC converter, I'm using a Keysight MSOX 6004A. It's a 4-channel scope, which is a really good scope. And on the right side here, I'm using two of the Keithley's SMUs. So this is the Keithley 2450, the Keithley 2460. I've done extensive reviews and teardowns of these units. These are absolutely brilliant source measure units. The bottom one, the 2460, is acting as the power supply for the DC-DC converter, and the 2450 is acting as the load. So at the same time, we're going to be able to see power in, power out, and voltage in, current out. On the right side here, I'm using an AM503B, which is a current amplifier for a current probe from Tektronix. It's a fairly old unit, and that's used over here in order for us to be able to measure the current going through the inductor of the DC-DC converter. Everything else is pretty self-explanatory. The output of the DC-DC converter, which is at 3.3 volts, is being shown on the oscilloscope as well. This will allow us to see the ripple at the output of the converter. And the voltage of the switching device of the MOSFET inside the DC-DC converter circuit here is also shown on the oscilloscope. So now that you have an idea of how the setup looks like, I think it's important to know exactly the principal operation of this DC-DC converter so we can understand and analyze the measurement and experiment we're about to do. So here's the very simplified block diagram and schematic of the buck converter that we're going to be using. Now, as you know, for a buck converter, DC-DC converter like this, you have the input and the output separated by a switching device. Now, the switching device in this case is an N-channel MOSFET built into the TPS54160, which is a Texas Instrument part. The diode is on the board, and the inductor is on the board, and of course the capacitors are on the board. So now the issue is, well, where does the losses of a system like this actually come from? Well, if you think about it, everything in this schematic is lossy. We have losses in the diode, we have losses in the inductor, we have losses in the N-channel MOSFET due to various imperfections of these devices. If I could make a perfect inductor, a perfect diode with 0-volt transition and infinite rise and fall time, infinitely small rise and fall time for the switching of the MOSFET, the system will have no losses. But of course, we cannot do this. Now, in this case study, the equations that describe the theoretical losses of all these components are provided in this booklet, and they are primarily a function of the input voltage, output voltage, the load, and the switching frequency. Now, typically as the load increases, some interesting things happen to the efficiency of DC-DC converters, as we will talk about. So it's not a very straightforward transition between low current and high current, because different kinds of losses in a system like this become dominant across the load current of the system. So in our setup, we are able to look at, of course, the I out and V out, that's the power at the output, the V in I in, the power at the input. We can see the waveform of the N-channel MOSFET switching, and we can see the current through the inductor. That's because they have provided a particular path for us to put a current probe around a load in order to be able to see the exact load through the inductor. Now you have to be careful because the load through the inductor and the load through the device under test are not quite exactly the same. That's why they have a separate path for the inductor current. So all these tie in with the theory very nicely. This is why in the experiment sheet itself, once you get to do the experiment, you actually have an opportunity to fill this table with your measurement data and compare the experimental efficiency and the theoretical efficiency, which is provided in the theory background section. So if I go back to the theory background section, sorry for switching all of this, there it is. All these equations here, the loss formulas for MOSFETs and diodes and inductors are all given. If you look at it, they're mostly a function of currents and ESRs and switching frequencies and the voltage and the current that goes in and out of the DC-DC converter. So by plugging those equations in, as provided with the values in this table, you're able to now compare experimental and theoretical efficiency, and then you can explore how these things relate to each other, and more importantly, how they change as a function of input voltage and output current, which is of course the main parameter you are interested in characterizing a DC-DC converter. And the reason for that is because if you think about how these systems are used, let me go back to this diagram. If you look at most of the way these buck converters are used, you typically have a battery or some source of input and a source of output. Now, most mobile devices and components are going to have an enormous dynamic range in the power they're using depending on how they're being operated. Take, for example, the Apple Watch. When it's sleeping, it's drawing very little current, perhaps less than a milliamp. But when it is awake and is talking to an LTE network, it might draw as much as half an amp. So now you have a DC-DC converter system that needs to support 1 milliamp to half an amp, and with a very good efficiency throughout the entire range of operation. And to make matters even more complicated, the battery in the watch is going to deplete, and even though it doesn't have a very huge range of voltages, indeed it changes the input voltage to the whole system. So these things can become very complicated, and this is why this particular study is interesting. So in our setup, as I mentioned earlier, I'm using the Keithley 2460 as the input and the Keithley 2450 as the load, and this will allow us to measure the efficiency. But there's actually a couple of places in this setup where there is inaccuracies in our measurement that will lead to an error in our efficiency. Can you spot them? I'm going to give you an opportunity to figure it out. But if you look at it, it becomes obvious very quickly. If you look at the 2450 and the 2460, I'm not using 4-wire measurements on either of those, which means that the actual input voltage to the DC-DC converter at the input of the DC-DC converter is not exactly what is being displayed by the 2460. And of course, the voltage coming out of the DC-DC converter isn't exactly the voltage that the 2450 is using to calculate the dissipated power. The current is correct, of course, but the voltage is not, which means that the losses in the cable to our load and the losses coming from our power supply are not included in the efficiency calculation, and both of those are going to hurt the efficiency of the system. But let's ignore that for a moment, and let's assume that those are not that important, even though at high current they can become significant because these cables are pretty long. But that's one source of error. If you wanted to avoid that source of error, what you'd have to do is measure the voltage directly across here and then the current, so that you don't have any losses in the cables. And the setup that they provide in the TI booklet uses all those components separately. That's why those losses will not be present in their setup. In order to fix it in this setup, we would have to use a sense port on both of these in order to be able to measure and sense the voltages exactly at the terminals, so that we can get rid of the losses in the cables. Some other minor bit of losses might be some of the coupling introduced by the current probe here directly from the current of an inductor is going to be fairly small, but that's definitely going to be present as well, and everything else is going to be fairly good. So now that I said that, let's go ahead and zoom over here and see what kind of numbers we're seeing on these instruments. So let's see what we have here. At the bottom, I'm providing 6 volts into the DC-DC converter, and it is consuming 0.74 watts. That is, of course, because we're drawing some current from the output of the DC-DC converter, and that's done by the 2450, which is drawing 200 milliamp. Now the voltage here is 3.3 volts. It's fixed by the DC-DC converter itself. So we are seeing the current and the power that the 2450 is absorbing, which is the power that the DC-DC converter is providing. So we have 0.65 watts and 200 milliamp. Well, we can calculate the efficiency of this by dividing this number by this number, taking into account, of course, that we're ignoring the losses in the cables. And these numbers are negative because power is going into the 2450. So let's do that. 0.65 divided by 0.74, and multiply that by 100, and we get the efficiency of about 88%, which is pretty good. So right now the DC-DC converter is converting 6 volts to 3.3 volts at 200 milliamp with the efficiency of 87.8%. Great. Now, so what happens if I were to reduce how much current is coming from the DC-DC converter, meaning that I reduce how much current I'm drawing with the 2450? What do we expect? Now, generally speaking, the losses of the lot of components on a DC-DC converter are either linearly or quadratically dependent on the output current, meaning that the efficiency is going to get worse when you increase the current. So you would expect when the current is tiny that the efficiency would get much better. Well, let's try that out. Let's go really, really small. And let's see what happens here. So let's go 5 milli. Let's make sure it's negative over here. There it is. So now we can see what the new efficiency is. So now we're drawing 5 milliamp, and let's go ahead and recalculate the efficiency. So we have 0.0166 divided by 0.0224, and now the efficiency is only 74%. Why is that? That's because there are some components in a DC-DC converter, such as the losses of the charge in the gate of the channel, the losses of the core of the inductor, and some of the IC losses. They have nothing to do with the output current. Therefore, if the fact that I'm drawing 5 milliamp is actually going to hurt the efficiency because we are below the threshold of the losses of those components, and they become the dominant factor. In fact, if you think about it, if I turn this off completely and draw only, right now it's drawing 1 milliamp, then the efficiency is horrible, of course, but the reason is because we are drawing so little current from it that all the other losses from the DC-DC converter become dominant. And this is a known issue and a known problem with DC-DC converters, of course. And there are a lot of techniques to help alleviate that. And some DC-DC converters do some fancy nonlinear things to eliminate the losses with very little output voltage, when there is very little output current. So we can also go ahead and take a look at what happens to the waveforms under these two conditions, because that's also really interesting. So here are the waveforms of the DC-DC converter. At the top here on channel 1, we have the voltage and the gate of the MOSFET that's built into the IC. So when the voltage is high, the MOSFET's turned on, and when voltage is low, the MOSFET is turned off. Now the duty cycle of this waveform here is being measured at about 58%. Now this duty cycle is going to determine the output voltage with respect to the input voltage. Now of course the input voltage here is fixed at 6 volts and the output is fixed at 3.3, and that's going to give you a fixed duty cycle. Now if you look over here at the bottom, we have the triangular waveform, which is the current through the inductor. Now the current through the inductor is going to have this nice triangular linear behavior. Every time the transistor is turned on or off, you're going to have a linear rise or fall in the current. So when the transistor is turned on, you can see that the current rises up, and as soon as it's turned off, it's going to go back down. And this output is of course filtered out and then turned into a voltage at the output. Now over here, we have the AC coupled view of the output voltage of the DC-DC converter. Now this is because it's AC coupled, it's sitting across 0 volts here, and you can see every time there's a switch in the MOSFET, we're going to get a ripple, and this oscillation is going to happen. This ripple is the result of all the parasitics and the coupling and the imperfections of the PCB and the components, and this is one of the problems of DC-DC converters. There's also some small transient which is correlated to the inductor current. As you can clearly see, as the inductor current is dropping, we have this minor ripple as well. Now all these imperfections of DC-DC converters are one of the disadvantages of them, as opposed to low dropout regulators, which of course do not have this problem. Now sometimes people go through extreme lengths and they build a DC-DC converter in order to bring a very high voltage to a very low voltage. Let's say they want to go from 24 volts to 3.3. They go from 22 to 3.5, and then they follow that by an LDO to bring 3.5 to 3.3. And that LDO's power losses are not going to be minimized, but it's because of its huge power supply rejection ratio, we're going to be able to filter that out, which is really interesting as well. So if you have, for example, both of these kits, the Buck and the LDO, you could put them in sequence and see the improvements that you get from filtering that comes from a low dropout regulator. So having said that, now what happens to this waveform if I were to change some of the parameters of the system? For example, let's go ahead and increase the input voltage to the DC-DC converter, meaning that instead of going from 6 volts to 3.3, let's go from 12 volts to 3.3. What do we actually expect to happen? Well, the only thing that's going to be immediate right away is going to be the switching transition here, because we no longer can use a 58% duty cycle. We're going to have to use a completely different duty cycle, which means that the transistor needs to stay on for a much shorter amount of time because the input voltage is now so much higher. So let's give that a try. All right, I'm going to go ahead and change the voltage. So right now it's at 6 volts. I'm going to type in 12 volts and here it is, and check it out. Now two things happen which are both very interesting. Let me go ahead and change that and this as well. And let's discuss what is actually going on. So let's go ahead and break this waveform down and to understand it. So this yellow line here is the switching of the transistor. Now the duty cycle of this waveform is now significantly smaller than it used to be before, which means that the transistor is on for a much shorter time than it used to be. And why is that? That's because the input voltage to the DC-DC converter is now much higher, meaning that the transistor needs to stay on for a much shorter amount of time in order to absorb energy from the source and produce a fixed 3.3 volt output. The change in the duty cycle is consistent with the fact that the input went up, but the output voltage stayed constant at 3.3 volts. So that part of it makes sense. But what is going on over here? Well, it turns out that when the output current is very small with respect to the input voltage and the input current, the DC-DC converter enters a new mode of operation called discontinuous conduction mode. In that mode, the current in the inductor reaches all the way down to 0. And you can clearly see that. It reaches all the way down to nothing. Now, when that happens, there is a resonance formed between the inductor and the parasitics of the diode and the transistor itself, and that creates ringing, and that ringing frequency is going to be determined by the natural frequency between the inductor and the parasitic capacitances. This is somewhat undesired because you can see some of that leaking to the output, and that noise will appear to the output. So how do we avoid that? Well, it's quite difficult to avoid this, because if the output of the converter requirement current is so small, you're going to enter this discontinuous conduction mode, and there are some techniques to avoid that. But the most important thing is that the efficiency calculation is now completely different, because these waveforms no longer have the original shapes, and therefore you need much more complex equations to describe the losses of these components. And many of the losses that used to be, like the losses in the switches and so on, they all disappear, and some other loss modes are going to be dominant. So the calculation of the efficiency is going to be very different. But now that we know this behavior, we should be able to modify these waveforms as we want by changing different parameters. So for example, let's see if we can bring it out of this continuous conduction mode. How do I do that? Well, I'm going to sink more current from the DC-DC converter to not allow the inductor current to reach 0. Let's go ahead and give that a try. So instead of 0.2 amps, I'm going to take 0.4 amps. Let's give that a try. Here is 0.4 amps. And there it is. You can see I have completely eliminated the discontinuous operation mode over here. Now we have the regular waveform back exactly as we were expecting it. The duty cycle is 30%. If you remember, the duty cycle used to be 58% when the input voltage was 6 volts, which means that if I were to change the input voltage, I should be able to change the duty cycle. So instead of 12 volts, let's give it 10 volts. And check it out. 36%, the duty cycle went up because the input voltage went down. Instead of 12 volts, let's go to 14 volts. And check it out, 26%, it went down. This is all consistent with exactly what we were expecting. Now, if I were to reduce the current back down, and if I go even lower, I should be able to put this into a much longer discontinuous mode of operation. Let's go to 0.1 amp. And there it is. Look at that. That is now a very long time to stay in this continuous conduction mode. And you can see it starts right when the inductor current reaches 0. And this leaks to the output as to be expected. And of course, this is a type 2 system, because the inductor and the losses of the capacitances of the transistor, these are not perfect. They're going to have resistive losses. So this is going to have a decay associated with it. This cannot go on forever. But everything else makes perfect sense. This duty cycle calculation is incorrect. Don't get confused by that, because there's some ringing going on over there. One thing I want you to keep in mind and not get confused about is that do not get confused about this duty cycle having anything to do with the output current. It has nothing to do with that. Changing the output current has no influence on this. So let me show you. Right now we're drawing 0.5 amps. I'm going to change it from 0.5 amps to 0.4 amps. You can see the duty cycle is 26%. It's completely unchanged. Let's increase it from 0.4 to 0.8. Let's double it. Here's 0.8 amps. And you can see no change. So the issue is not the output current. The issue is the ratio between the input voltage and output voltage. So this evaluation board also gives us the ability to change the frequency of the DC-DC converter. So right now we're running at 250 kilohertz, and if I place a jumper, I can change the frequency, and then the number of times the device switches will double, go to 500 kilohertz. Let's give that a try. And look at this duty cycle here, it's 26%. I'm going to increase the frequency. There it is. It's still 26%. Of course, that makes sense, because only the duty cycle is, as I said, the ratio of the input to the output voltage. But now the frequency is double, which means that several other things come into play. The spectral content of the noise of the output of the DC-DC converter is going to be different. So why would you increase the frequency? Because the losses of the inductors and other things also get worse. Well, that allows you to miniaturize things. So the frequency has some other advantages, because the component values can be different. So there is a trade-off between loss, efficiency, noise, and everything with the switching frequency of the converter itself. That's one of the other topics that's discussed in the booklet. So as you can see, this is really, really fun to play with. There is so many experiments. There's so many other different things to worry about. They talk about the losses in the inductors. You can actually change a jumper over here to use two different kinds of inductors and explore the losses that the different inductors have. It's really quite elaborate. And all the waveforms are given so that you can verify that what you're measuring on the instrument makes sense with proper explanation of everything there. I'm really impressed. It's not easy to put something like this together, and I hope that you enjoyed this video and got you excited to go and check the TI's university courses, not just for this one but also for the other ones, but in particular for DC-DC converters, as they are such critical blocks in today's design, and many devices use them. If you like this video, let me know. If you want me to do more DC-DC converter experiments using this kit, let me know as well. And if you happen to engage in these activities because of the video, let TI know. This allows me to get more of their university courses and show you more demos in the future, which I think is quite exciting. And as always, I really appreciate the Patreon support. There's going to be lots more giveaways. Some of them are going to be particular for my Patreon supporters, so that's going to be coming up. I hope you enjoyed this video. I'll see you in the comment section.